So we're in section 14.3. All right, so what we're going to do is kind of develop the idea of a double integral when we're talking about polar coordinates, doing the same thing that we did with rectangular coordinates, figuring out what our little elements of area is in the polar plane, just like we did for our area element in the xy plane. A lot of integrals that are difficult to evaluate in rectangular coordinates become much easier in polar coordinates. So let's just do a quick reminder, not that I think that it's totally necessary, but just to kind of refresh our memories about polar coordinates. We have x equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared. These are just relationships that we use fairly often in polar coordinates, and tangent theta is y over x. So those are our main relationships in polar coordinates. So let's look at a sector, a section, a small area of the polar plane, and come up with how we are going to write our area increment. So this is our pi over 2 axis. This is our theta equals 0. So what we're going to do is take this and we're going to divide. We're going to draw a picture of a little region in polar coordinates. So we're going to look at this region. And we're going from theta equals alpha to theta equals beta. And we'll call this, we want to call that R1 and R2. We'll say this is R equals A, and this is R equals B. So this little section here, this little piece of this region is going to be delta R. The length of that segment is delta R. And this piece in here is delta theta. We're going to look just at this sector. We want to find the area of that sector. And we're going to think of it as a polar rectangle. So the area of a circular sector So a ring, essentially. I'm sorry, a sector where I'm not talking about a ring yet. Just the sector, the area of a circular sector. If we have our angle as theta, is area equals 1/2 r squared theta. So if we just have a sector, that's going to be the area. And the area of our region here is going to be the difference in the areas of the circular sectors from r equals A to r equals B. So our area is going to be 1/2 b squared delta theta minus 1/2 a squared delta theta. So we're just finding the area between of the one circular sector minus the other circular sector to get this one. And I'm going to rewrite that as a equals 1/2 b squared minus a squared delta theta. And then we're going to factor b squared minus a squared. So our area is 1/2 a plus b times b minus a delta theta. And this quantity 1/2 a plus b is just the average. We can think of that as the average radius in our sector. So a equals r, and I'm going to use the bar for our average radius. And b minus a is just delta r. And I'm going to say r equals average radius. So that's how we're going to represent the area of this little region. If we want to find the volume underneath a function a surface that's up above the plane, we're just going to multiply the area of the base times our height and sum that over the region. So if we want to find the volume here, we have a surface up above. We're going to say, is everybody good with where we are so far? So we're going to say is the volume under f of xy bounded by r is f of x sub I, y sub I, delta a sub I, where the I represents our little region R. And we said that our area of our region, delta A, is the average radius, putting a little arrow on there, in that region, times delta R sub I, delta theta sub I. And if we express our function in polar coordinates, we convert our x's and y's to polar coordinates, we're going to say that the volume is f of r cosine theta, r sine theta, and this should be theta sub r sub I and theta sub I, because we're looking at each little region, times the average radius in that region, times delta r sub I, delta theta sub I. And if we're looking at an entire region, so this was a small, if we subdivide our region into smaller and smaller and smaller little pieces, where we have different delta theta sub i's, delta r sub i's, and the average radius, we're going to subdivide our region, and to find the volume over the entire region, we're going to sum all these little volume elements that are represented by this. So the entire volume, and I guess we should say, rather than V, we should say delta V, because this is a part of the volume. So we're going to sum the volumes over the entire region. We've subdivided it into these little polar rectangles, and sum to find the volume over the entire region. Is the sum I equals 1 to n, however many little subdivisions we make. of this quantity. F of r sub I cosine theta sub I, r sub I sine theta sub I, and our little area element. And then we take the limit as the size of our little polar rectangles gets smaller and smaller. And again, I'm being a little loose with our terminology. When we take the limit, the size of the polar rectangle, we say that the length of the longest diagonal of any of the polar rectangles is approaching 0. So that's what we call the norm of the region. So that's what we're talking about when we talk about this limit, is that longest diagonal is going to 0. I'll just say delta A goes to 0. So if we take the limit, this corresponds to our definition of a double integral. This is exactly how we defined a double integral, is the limit of this quantity. So we're going to say that the double integral over our region of f of xy dA is approximately the sum that we just talked about, I equals 1 to n, of our function in polar coordinates and as our subdivision gets smaller and smaller, the average radius just becomes the radius of that tiny little polar rectangle. So we don't have to worry about the average radius anymore. It's so small that the radius of that little region is just the radius that we're talking about. And we say in polar coordinates that our double integral of r of f of xy dA is, and I'm going to write double integral s, and we write s in polar coordinates to remind us that we're using polar coordinates rather than rectangular coordinates, of f of r cosine theta, r sine theta, r dr d theta. So in polar coordinates,
Is this r or is it average of r?
well, when we take the limit, when we let the delta A get smaller and smaller and smaller, r is just the radius of that tiny little polar rectangle. In polar coordinates, you will always have that quantity in your as part of your integrand. The quantity in your little increment of area in polar coordinates is always r dr d theta. You can do it the other order, but it will always include the r, the dr, and the d theta. So all three of those quantities are always in your integrands for polar coordinates. It's easy. Often students will forget that this extra r in polar coordinates. So just think dr d theta. So it's an easy one to leave off. But that r dr d theta is always included in your integrand in polar coordinates. And we can switch the order. just like we can in rectangular coordinates, but r will always be in there. And whenever we get to this point, I remember there was a Simpsons episode where Lisa goes to a really advanced school, and they're doing calculus, and all the students start laughing, and Lisa doesn't understand. And it's because they were doing an integral, and the integrand included RDR. And the students all thought it was funny, but Lisa didn't get it. All right. So questions on our development here. So now we know what a double integral in polar coordinates is. It's this quantity. This just like we did in rectangular coordinates. This doesn't tell us how we evaluate a double integral in polar coordinates. We know what it is. We don't know how to evaluate it. Well, you're going to use a theorem similar to Fubini's theorem that we used in rectangular coordinates. Really tells us the same thing in terms of evaluating these integrals, double integrals in polar coordinates. So to evaluate, just like we would expect, so R is our region. So R is a region of points, and we have whose polar coordinates we have a couple of different cases, just like we did in rectangular coordinates. We're going to say that our double integral of f of xy dA is the integral. So I didn't put my coordinates in here. For the first set, alpha is less than theta is less than or equal to beta. So theta varies from alpha to beta, and our radius is some function of theta. So our double integral here is going to be the integral from theta equals alpha to beta. The integral r equals g1 of theta to g2 of theta. We transfer our function into polar coordinates, our cosine theta, our sine theta, and our order is going to be here r dr d theta. And we call this a radially simple region. So our region here is going to look something like this. So our theta varies from two set values, and our radius is some function of theta. So this would be a radially simple region. And you'll sometimes see this called R simple also. And our second condition is when we have some function of theta and we switch our order. So for our second condition, A is less than or equal to R less than or equal to B, and H1 of R is less than or equal to theta less than or equal to H2 of R. So we have theta as a function of R, and we're just going to switch the order here. So our integral over our region, double integral is just going to be the integral from a to b. h1 of r to h2 of r are inner limits, and our function in rectangular coordinates are d theta dr. And we call this kind of region angularly simple. And our region is going to look like this. So essentially what we're doing here is dividing our region into little rectangles that go from one radius to the other, and here we're dividing our region into little rectangles that go from one angle to the other. So this is how we evaluate double integrals in polar coordinates. Just like we do in rectangular coordinates. So any questions on this? On the development? So again, often the difficult part in polar coordinates is figuring out what your region is, figuring out the limits of your integration, sometimes changing your function from a function of x and y to a function of r and theta. And then of course when we integrate, we have trig functions, so sometimes that makes it a little more difficult, but often integrating the trig functions in polar coordinates is easier than integrating the functions in rectangular coordinates. All right, let's look at a few examples. So, here's our double integral that we want to evaluate. So we have this integral. We want to change this to polar coordinates, so we want to evaluate in polar coordinates. So let's draw our region. The limits of integration say y varies from 0 to the square root of a squared minus x squared. So what is our function? What's it going to look like? Circle radius a centered at the origin, right? So we have something like this. There's our function, and x varies from 0 to a. So this is a, and this is going to be a. So that's our region. So we want to switch that to polar coordinates. So if I draw a little rectangle like so, probably don't even need to draw a rectangle. What is r going to vary from in this if we switch this to polar coordinates? Our radius is going to vary from 0 to a. 0 less than or equal to r less than or equal to a. And how about theta? 0 less than or equal to theta less than or equal to pi over 2. So I'm just going to integrate. If I transform this into polar coordinates, our integral becomes the integral from 0 to pi over 2. integral from 0 to a. And x is just r cosine theta. R dr d theta. And this becomes, if I rearrange, just end up with 0 to pi over 2, integral from 0 to a of r squared cosine theta dr d theta. Not a difficult one to evaluate. The inner integral, we just evaluate r cubed over 3 from 0 to a, and the outer integral, we evaluating the integral of cosine theta d theta. So this one's an easy one to evaluate. This one we would end up having to do some trig sub to evaluate.
So is that why you would change the polar and not give it a polar?
Definitely, definitely. Yeah, if you have some kind of circular region, chances are your integral is going to be way easier to evaluate in polar coordinates. So if you have a region that has some kind of circular symmetry, that's going to be a hint that you want to change the polar coordinates. Yeah.
We just use u sub to be the derivative of a squared minus x squared times x.
Let's see, a squared minus x squared. Yeah, I guess this one wouldn't. So we wouldn't need the trig sub. And then we'd have to evaluate the x integral. Oh yeah, we'd have x squared on the outside, right? When we'd end up with an x squared on the outside. All right, questions on that one? All right, let's look at another one. We want to find the volume of the solid bounded by z equals x squared plus y squared plus 3, z equals 0, and x squared plus y squared equals 1. So we want the volume bounded by this solid. Our region in the xy plane is a circle. So that's a hint that I might want to use polar coordinates. Our z, our function, our surface has this x squared and y squared in it. So that's a hint that I might want to use polar coordinates. So let's sketch our region in the xy plane. Z equals 0 just means that we're looking at the portion above the xy plane. So here's my region in the xy plane. My radius is 1. And I sketched a quarter of the region. So this is 1/4 of r. And if I change my function z equals x squared plus y squared, z equals x squared plus y squared plus 3, how would I represent that in polar coordinates? Z equals r squared plus 3. In the xy plane, I'm going to say 0 is less than or equal to r less than or equal to what here? 1. This gives us our region. And 0 less than or equal to theta less than or equal to 2 pi. And I'm just going to do a quarter of the region and multiply by 4 since it's symmetrical. 0 less than or equal to theta less than or equal to 2 pi. And I'm just going to evaluate the integral on this quarter and multiply everything by 4. So our volume is going to be 4 times the integral from 0 to pi over 2, integral from 0 to 1. And if it helps, you can, and when we get to triple integrals it might help, you can write, just as a reminder, theta equals and r equals, to remember what you're talking about here. our function is just going to be r squared plus 3. That's our height above the xy plane, and r dr d theta. And this is a nice, easy integral to evaluate. Questions? When we evaluate this, I'm not going to go through the entire evaluation. We come up with 7 pi over 2. But this is not a difficult one to evaluate at all. All right, so let's do one more, little more complicated example, and then we will be set. So for this one, we want the volume inside the hemisphere z equals square root of 16 minus x squared minus y squared. And outside x squared, the cylinder x squared plus y squared equals 1. So we want to be inside this hemisphere and outside this cylinder. So if I make a quick sketch of this region, and I'm just going to sketch it in the first octant. So there's our hemisphere. And there's our cylinder. So we want the part we're looking for the volume of this hemisphere after we drill a hole through it, basically. So we're drilling a hole through it, which is our cylinder, and we want the volume that's left over. And we want to find that with a double integral. So this is what it looks like in the first octant. In the xy plane, we have just concentric circles. The cylinder x squared plus y squared equals 1 takes us here, and the hemisphere, the radius of the hemisphere is 4. So we're finding the volume that's underneath our surface inside this little strip. So this is our 1/4 of our region again, just like in our last problem. So our region would be all the way around in all 4 quadrants. So we're just going to transfer this to polar coordinates. So z in polar coordinates is going to be what? 16 minus r squared. And our limits of integration are going to be nice and easy here. So our volume is going to be the integral. Theta is going to vary from what to what? 0 to 2 pi. And let's just it's a symmetrical situation, so I'm going to do just this first quarter and multiply by 4. 4 times the integral 0 to pi over 2. R varies from 1 to 4 of square root of 16 minus r squared r dr d theta. We have a nice, for our r integral, we have a nice u substitution because we have an r squared here and an r outside the radical. So we just end up with a u sub for the first one. And then our theta integral is just from 0 to 2 pi. Nice, easy integrals to evaluate here. And when we evaluate them, I'm not going to go through the evaluation. It ends up to being 10 pi square root 15. But our integrals, nice integrals, not too difficult. Questions on that example? And I'm thinking back, I'm looking at this one and thinking about this one in rectangular coordinates. I don't even like the way that thinking about how it's going to end up looking in rectangular coordinates. Because we're going to have all these radicals. X is going to vary from 0 to, or so we're going to have a radical in the x integral. It's going to be an ugly integral, I think. All right, any questions? Okay, I have a couple of questions for you. So we want to find this double integral, the value of this double integral. And what I'm going to say is, do we want vertical elements? Actually, I'm not even going to say that. How do we want to set up our? How would we for the region that I sketch out? How do you want to set up your integral? Or how could you set up your integral? We're talking either vertical, horizontal, rectangles, or polar coordinates. So how would you set up your integral for that region? Horizontal rectangles could work because our rectangles would go from whatever this line is over to whatever that function is. Could we do it another way? Polar? Because polar would be, theta would vary from 0 to whatever the angle is here, and r would vary from whatever our radius is here, out to the radius, this as a function of theta.
Do the angle from 0?
Yeah, so our angle would vary from 0 here, and it would go, so if I sketched out one of the radius sweeping out, it would sweep here, here, here. Those would be our little sectors. So we could do it horizontal rectangles, or polar could work, depending on what the functions are. How about this region? My curvy x-axis there. How about that region? Polar, definitely, right? That looks exactly like the polar rectangles that we use to set up our polar integral. All right, last one. How about that one? Polar or vertical? So this is just like this one turned on its side. So this would be,
What would be an example when you want to switch the order to polar?
Yeah, it doesn't really happen that much because usually we're given some function, or we can easily change our function into the radius as a function of theta. Really the only example that I can think of is if we have theta varying as the radius varies. So we had some kind of region that was where theta varied and our radius was fixed. Just like the picture I drew before, but the vast majority of the time, it's your order is going to be r d theta, because usually we have our radius as a function. We can express our radius as a function of theta. All right, any other questions? Okay. We're in the thousands now. There you go.